Well, there's a flip side of exponential growth. It's exponential decay. Sad. Yeah, and so not everything grows in accordance of multiplication, right? Some things get smaller. The example that we did in class was like the bouncy ball, right? So if you drop a bouncy ball, let's give it a ridiculous height. Let's say we throw a bouncy ball, and this is like a pretty awesome bouncy ball. We drop it from a height of 1,000 feet. Well, maybe instead of coming all the way back down, it only comes up a portion of the way, as you'd expect. Let's say that each time it returns like 62% of its bounce, right? So if it returns 62% of its bounce, the next time it'll only bounce a little bit higher, a little bit higher, a little bit higher, a little bit higher, and boing, 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 boing. You guys have all seen these things work. If I was to graph just the top parts of these bounces, you'd see this kind of curve. And in fact, that's what an exponential decay graph kind of looks like. Right? So now what do I want to do? Exponential decay. Well, let's take that example. If I start off with a height of 1,000 feet for my first drop, and it returns 62% of its bounce, I need to convert this into a decimal, which is 0.62. So I start at 1,000, and after my first bounce, what's the height? Well, exponential decay is still that multiplication thing, right? Still, I still find the sequence through multiplication, and now I'm going to be multiplied by 0.62. So 0.62. So 1,000 times 0.62 is 620, and that makes sense, right? It'll only bounce up a little bit more than half because 62% is a little bit more than half. Well, I can find the next one in the sequence after the second bounce, right? By just multiplying that again, and I get 384.4. And I can do it a third time and say, okay, what is this? Multiply by 0.62, and I get 238. So our bouncy ball is losing, but this time it lost like 400 feet in its bounce. This time, a little less than 300, and this one a little more than 100, right? So it keeps losing a little bit less each time. If I wanted to make an equation out of this, I need to think about what I'm doing, right? So let's say I want to find it after 7 bounces. So after 7 bounces, what would I be doing? Well, I take 1,000 times 0.62 times 0.62 times 0.62 times 0.62, dot, 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 dot. And how many times would I be doing that? I'd be doing that 7 times. So it's 1,000 times, and I'm going to write times like this, 0.62, and I'm going to do that 7 times, right? Write that a little bigger. So this is a nice way of saying after 7 times. Well, to make it more general, I mean, how many times would I have to do it after any amount of bounces? Well, that's the part where the x comes in, right? I could plug in a 5, and this would give me an output of 5 bounces. I could put in a 12, and it would give me 12 bounces. You can make a table very easily off this, right? And say, okay, well, I'm going to start with 1,000, right? And I'm going to multiply by 0.62 to the x power, right? And let's just make a table and kind of see what's going on. So I'm going to use a table that's underneath the graph thing, so second table. And you can see all those values confirmed, right? Actually, you can't see it because this is not, there we go, that's not very effective. And you can see it going down. Well, you can scan down this list as far as you want. And you're going to notice the numbers get really small, but they don't necessarily ever hit 0, right? It's like taking a piece of paper or this Kleenex, right? And if I take this Kleenex and I rip it in half over and over and over again, I'll always have something to rip, right? So exponential decay, in this case, I mean, it's a really good modeler of it, but there's a difference between the theoretical and the actual, right? If you keep going on that list, the bouncy ball is always going to return a little bit of bounce, right? And it'll never stop bouncing. Just like I could keep cutting this thing in half and never actually really reach the end of it. Another kind of example of exponential decay, or another way of phrasing it, is let's say you you bought this nice truck, right? So you bought this nice truck, and the truck it cost $15,000. Well, as soon as you buy a truck, it starts losing value, right? So let's say that it loses 11% of its value every single year, right? So how can I model this equation? Well, I want to start at 15,000. The question is, what is it the next year? Right? So the key to these problems is, sure, it loses 11%, but the real question that I need to figure out is, well, how much does that leave as a return, right? Well, if it loses 11%, that means it is only worth 89% of what it was before. And 89% is 0.89. So what you want to do is figure out how much is left. Right? And so if I multiply, and so this will be my multiplier. So each time I'll multiply by 0.89 over and over again. Right? So 15,000 times 0.89, that means after the first year it's $13,350, worth $13,350, right? And so on and so forth. So this equation can be modeled by my starting point of 15,000 times every year it's going to lose 11%, and this is what it looks like to lose 11% to the x power. If you need a more formalized way of doing that, remember in exponential growth how we said, well, we get 100% of it, and we like gain 8% each year, so that's why gaining 8% looks like this. Well, the same thing holds true. We're losing 11%. Well, that's minus 0.11. Well, guess what 1.00 minus 11 is? Well, 0.89. Right? So these exponential growth situations, that's how you can find the what number you need to multiply by.